In the heart of the 18th century, science seemed untouchable, a fortress of certainty. Every experiment, every conclusion, every carefully measured observation was assumed to reveal the absolute truth. The world appeared orderly, logical, predictable. And yet, one small, unassuming experiment would shatter these assumptions, forcing scientists to confront a reality they had been completely blind to. What they discovered would overturn centuries of understanding and leave humanity questioning the very nature of life itself. Europe in the mid-1700s was a continent alive with intellectual fervor. The Enlightenment had ignited curiosity in every corner of society. Philosophers debated the mysteries of the universe in candlelit salons, while scientists meticulously measured, calculated, and catalogued every observable phenomenon. Knowledge was expanding faster than ever, yet some truths remained tantalizingly out of reach. One of these truths concerned something so fundamental, so ordinary, that it had escaped scrutiny for generations: the behavior of living tissue when exposed to external forces. Until that moment, the prevailing belief among scientists was simple. Life could be explained mechanically. Muscles moved because of chemical reactions. Nerves carried signals like biological wires. Everything in nature followed predictable, measurable laws. Yet one man's curiosity would challenge this notion and, unknowingly, set the stage for a revolution in understanding the relationship between life and electricity. Luigi Galvani, an Italian physician and anatomist, was a man driven by insatiable curiosity. Bologna's streets outside buzzed with commerce and chatter, but within his modest study, Galvani pursued questions most scientists deemed irrelevant or impossible. He was fascinated by electricity, not as a tool for powering devices, but as a potential force animating life itself. His obsession began with frogs, humble creatures overlooked in the grand hierarchy of living beings, yet destined to become the instruments of revelation. Galvani's earliest experiments were meticulous. He carefully dissected frogs, exposing their nerves and muscles, and observed how they reacted to various stimuli. One evening, as he connected a nerve to a metal probe, the frog's leg twitched. Not a subtle movement, but a sudden, almost lifelike kick. At first, he questioned the result, blaming faulty technique or a fluke. But repeated experiments produced the same astonishing effect. The dead tissue moved as if commanded by an invisible hand. It was as though electricity itself could awaken life, even in a body long since silenced. Word of Galvani's discovery spread through the academic circles of Europe, provoking both awe and skepticism. Some hailed it as a glimpse into the hidden forces animating all living beings. Others dismissed it as an illusion or misinterpretation, clinging to the prevailing notion that life could be entirely explained through chemistry and mechanics. Yet the evidence was undeniable. His observations were precise, reproducible, and deeply unsettling to the scientific status quo. Galvani's nephew, Giovanni Aldini, would later carry the work further, transforming fascination into spectacle. Aldini conducted public demonstrations in which cadavers connected to rudimentary electrical apparatuses twitched and convulsed under electric currents. The reactions were so striking that audiences gasped, half in horror, half in awe. One of the most infamous events took place in London in 1803. A recently executed criminal's body was subjected to electrical stimulation, and witnesses described the limbs jerking violently, the facial muscles contorting, as though the dead man were briefly returned to life. Scholars debated furiously, some lauding it as evidence of a vital force, others condemning it as grotesque theater. Amidst this heated debate, a quiet figure entered the scene. Alessandro Volta, a fellow Italian and contemporary of Galvani. Volta approached the phenomenon not with the eyes of a biologist, but as a physicist, a man attuned to the mechanics of electricity itself. To him, Galvani's conclusions were flawed. The movements observed in frog muscles, Volta argued, were not evidence that electricity animated life, but rather that the metals used in Galvani's experiments produced a chemical reaction that caused the twitching. In essence, the experiment's results were real, but the interpretation, the notion that electricity itself was the spark of life, was entirely mistaken. Volta's investigations culminated in the invention of the voltaic pile, the first true battery. With it, he could generate a consistent, controllable electric current without involving any animal tissue. By demonstrating that electricity alone could cause muscle contractions, Volta proved that the twitching was not a sign of some mystical vital force, but a physical phenomenon entirely separate from life. Galvani had observed a real effect, yes, but his interpretation, once celebrated and accepted, had been wrong. Scientists were forced to confront a humbling truth. Even careful observation can mislead when the framework of understanding is incomplete or biased by prior assumptions. The implications of this revelation were enormous. It challenged the dominant mechanistic view of life, opening the door to entirely new ways of thinking about physiology, neurology, and bioelectricity. Over the next century, researchers explored the electrical properties of the nervous system, eventually leading to breakthroughs that transformed medicine. Pacemakers, defibrillators, and countless neurological treatments trace their roots back to these experiments. Galvani's frogs, once merely a curiosity, became the cornerstone for understanding how electricity interacts with living tissue. Yet beyond the scientific impact, the episode serves as a profound lesson in the philosophy of science. Observation alone is never enough. Data must be interpreted with care, and conclusions must always remain tentative in the face of new evidence. Galvani's story reminds us that human understanding is provisional, a constant negotiation between what we see and what we believe we know. Even brilliant minds, armed with meticulous experiments, can be misled by the assumptions they carry into their work. The historical context amplifies the drama. The 18th century was not just a time of scientific advancement, but of political upheaval, social transformation, and cultural renaissance. Universities were expanding, knowledge was becoming more democratized, and the tension between tradition and innovation was palpable. In this environment, an experiment that contradicted centuries of accepted wisdom did more than challenge scientific dogma. It unsettled the very intellectual and cultural frameworks of the era. Scholars debated in salons and lecture halls, students whispered in corridors, and the broader public, fascinated by both science and spectacle, grappled with the possibility that even the experts could be wrong. Galvani himself was a man of paradox, deeply meticulous yet open to wonder, cautious yet daring. He embodied the contradictions of the Enlightenment. He pursued knowledge not merely for acclaim, but out of a profound curiosity about the natural world. His experiments were humble in appearance: a frog, some metal wires, a spark of electricity. Yet the consequences of his observations would reverberate across continents and decades. In Galvani, we see both the triumph and the vulnerability of human intellect, the capacity to observe the subtle secrets of nature, and the risk of interpreting them through the lens of existing beliefs. The ripple effects of Galvani and Volta's work extend far beyond 18th century Europe. They influenced the study of bioelectrical phenomena, informed early experiments in chemistry and physics, and inspired future generations of scientists to challenge assumptions boldly. Perhaps most importantly, they remind us that science is not a linear march toward truth, but a dynamic, sometimes messy, iterative process. Hypotheses are proposed, tested, challenged, and revised. Mistakes are not failures, but essential steps in the collective pursuit of understanding. Even today, the story of Galvani's frogs resonates. Modern neuroscience, electrophysiology, and medical technology all owe a debt to those twitching limbs observed centuries ago. The experiment that seemed so simple, so almost trivial, taught a profound lesson. Reality does not always conform to expectation, and truth can be stranger, subtler, and more elusive than the mind initially perceives. Galvani's curiosity, combined with Volta's critical insight, exemplifies the duality at the heart of scientific progress. Observation and interpretation must coexist, and humility before nature is always required. In the end, the twitching frog legs were more than a biological oddity. They were a mirror reflecting the limitations of human understanding. They revealed that certainty can be an illusion, and that even the most trusted authorities can be wrong. The experiment became a milestone in the history of science, a vivid reminder that the pursuit of knowledge is as much about questioning as it is about discovering. As we reflect on this story today, it challenges us to embrace curiosity, rigor, and an openness to being proven wrong. It reminds us that the natural world is infinitely complex, and our understanding, no matter how sophisticated, is always provisional. Galvani's experiment stands as a testament to the courage required to explore the unknown and to the humility needed to accept that nature often defies expectation. The legacy of that small experiment in a dimly lit Bologna laboratory is everywhere. From the electrical stimulation of muscles in modern physiology labs to the life-saving technology of cardiac devices, the echoes of Galvani and Volta's work resonate. And perhaps most importantly, their story teaches an enduring lesson that progress is born not from unquestioned certainty, but from the relentless pursuit of truth, tempered by the willingness to acknowledge when we are wrong. Science, at its best, is a conversation across time. Galvani spoke through twitching frog legs. Volta responded with the language of electricity. Together, they forged a dialogue that continues today, reminding us that discovery is never a solitary achievement, but a collaborative, evolving endeavor. The experiment that proved scientists were completely wrong was not a failure. It was a triumph of inquiry, observation, and the courage to challenge even the most deeply held assumptions. And so, the next time you encounter a scientific fact, remember Galvani's frogs and the spark that ignited a revolution in understanding. Remember that even centuries of consensus can be overturned by a single experiment, and that curiosity, rigor, and humility are the truest paths to knowledge. The story of the experiment that shook the foundations of science is a story of human ambition, wonder, and the relentless quest to uncover the hidden truths of the world. Truths that are often stranger and more extraordinary than anything we could have imagined.